Hello there, and welcome to Physics with William, where we dive into the curious and often perplexing world of science. Today we're going on a journey to explore one of the most captivating questions humanity has ever pondered. Can we achieve infinite energy? It's a question that seems to echo through history, from the ancient myths of perpetual motion to the ambitious dreams of modern scientists. The idea of unlimited energy, a source that could power everything without ever running out, has been an alluring thought for millennia. And in many ways, it's at the heart of some of the most ambitious scientific pursuits of our time. You've probably heard of the idea of endless energy before. It's the stuff of science fiction, the fuel for futuristic worlds where resources are limitless and everything seems possible. But what if I told you that scientists are actually making strides to answer this question? Of course, it's not a straightforward answer, and it requires a deep dive into the very fabric of how our universe operates. But it all begins with a rather fundamental question. What does energy actually mean? Think about the world around you. Every moment there's energy in action. The electricity powering your devices, the food you eat to keep moving, even the gravity that pulls things towards the ground. All of these are forms of energy. And yet, there's a concept that stands above all of these, one that challenges our understanding of how energy works. Could there be a way to tap into energy that never depletes? Could we unlock a source so potent that it can fuel humanity indefinitely? Before we get into the specifics of the cutting-edge experiments and breakthroughs in energy research, let me ask you something a bit more personal. Where are you listening from today? What time is it where you are? Isn't it interesting how time and energy are intertwined? We measure the passage of time by the energy we consume, whether it's through the ticking of a clock or the activities we engage in. Time, just like energy, is a force we live by, but also one that's difficult to truly define or control. Now, before we dive into the science behind the ALPHA experiment at CERN, I'd love it if you could take a moment to hit that like button if you find this conversation interesting. If you subscribe, it helps this little corner of the internet grow and reach others who might enjoy a peaceful, reflective dive into the wonders of the universe. Let's not waste any more time though. It's time to explore how we've come to ask the question, is infinite energy possible? And whether it's something within our reach. For centuries, humans have dreamed of achieving infinite power. It's the ultimate prize, a vision that stretches back to the dawn of civilization and has been woven into the fabric of our mythology, literature, and science. The idea of boundless energy has always held a certain magic, one that suggests not only limitless power, but freedom from the constraints of our natural world. It's a concept that sounds like something from a fantasy, but the allure of infinite energy is grounded in a very real desire to break free from the limitations we face on Earth. Imagine a world where energy is no longer a scarce resource. No more power plants burning fossil fuels, no more wind farms spinning endlessly in search of the right gust, and no more trying to figure out how to balance the delicate equation of supply and demand. In this world, everything from the smallest electronic device to the largest city grid could be powered effortlessly, without the need to constantly worry about running out of resources. This dream, while lofty, is not entirely beyond the realm of possibility. The truth is, we've been trying to figure out how to tap into such energy for a very long time. In the past, the idea of infinite energy was bound to myth and legend. One of the most famous stories is that of the Philosopher's Stone, the legendary alchemical substance said to be capable of transforming base metals into gold and granting eternal life. While it might sound like a fanciful tale now, the quest for the Philosopher's Stone was driven by a very real desire to unlock hidden powers of nature. Those alchemists and early scientists, in their quest for immortality and wealth, were unknowingly laying the groundwork for the scientific inquiries that would later shape our understanding of energy. As time passed, the dream of boundless power evolved. In the 19th century, the idea of perpetual motion machines gained popularity. These machines were designed to run indefinitely without any external input of energy, creating a cycle that could theoretically continue forever. The notion seemed simple. If you could just create the right mechanism, energy would flow forever without ever depleting. These machines would be a direct manifestation of infinite energy, offering a promise of freedom from the constant need to generate power. However, the pursuit of perpetual motion was met with obstacles. The laws of thermodynamics, the fundamental rules that govern energy and heat, made it clear that perpetual motion was, in fact, impossible. The first law of thermodynamics, which states that energy cannot be created or destroyed, only transformed, made it evident that a machine could not run indefinitely without eventually running out of energy. Similarly, the second law of thermodynamics introduced the concept of entropy, which describes how energy spreads out and becomes less usable over time. In other words, no machine could ever be perfectly efficient, and the idea of a machine that produces more energy than it consumes went against the very nature of how the universe operates. Despite these setbacks, the dream of infinite energy persisted, especially as we began to unlock more of the mysteries of the universe. The 20th century brought with it advances in nuclear energy, quantum mechanics, and the study of the fundamental forces of nature. Suddenly, what seemed like an unattainable dream was starting to look like something more within reach. Could we one day tap into sources of energy so vast and so powerful that they would seem to defy the very laws of physics? And that brings us to today, where new experiments and breakthroughs are being made in laboratories around the world. The dream of infinite energy is still alive, though it has evolved into something more focused and scientific. No longer are we chasing mythical stones or chasing after machines that run forever. Instead, we are looking at the fundamental building blocks of matter and energy, examining how they interact at the deepest levels. We're asking, what if we could tap into the immense power contained within the very fabric of the universe itself? Before diving into the cutting-edge experiments, let me ask you something. Have you ever thought about what it would mean to live in a world where energy is no longer a limitation? What would that kind of power look like? How would our lives change if we no longer had to think about where our energy comes from, or how we're going to power our homes, cars, or cities? I'd love to know what you think, and if you've enjoyed this exploration so far, don't forget to like and subscribe. Let's move forward and delve deeper into the science that's bringing us closer to the dream of infinite energy. Let's take a look at what the future of energy might hold, and whether CERN's ALPHA experiment is a step in the right direction. Energy is a concept that we encounter daily, but it's also one of the most fundamental and elusive ideas in all of science. In simple terms, energy is the ability to do work. It's what allows us to lift objects, light our homes, and power the devices we rely on. Energy is in everything, from the food we eat to the electricity that powers our cities. It drives the forces of nature, shapes the behavior of matter, and governs the way the universe functions. But even though energy is everywhere, defining it precisely isn't as easy as it sounds. Energy exists in many different forms, and understanding it requires us to recognize the diversity of those forms. The most common forms of energy we encounter are mechanical, thermal, electrical, chemical, and nuclear. Mechanical energy is the energy associated with motion and position, like a moving car or a rock at the top of a hill. Thermal energy, or heat energy, comes from the motion of atoms and molecules within substances, like the warmth from a stove or the heat we feel from the sun. Electrical energy is the energy carried by moving electrons, powering everything from light bulbs to computers. Chemical energy is stored in the bonds between atoms and molecules, and it's released in processes like digestion or the combustion of fuels. Finally, nuclear energy, the energy stored in the nucleus of atoms, is what powers the sun and nuclear reactors. But despite the many forms energy can take, all energy is ultimately measured in terms of its ability to do work. In a sense, energy is a currency that flows through every process in the universe, enabling the physical and chemical reactions that make everything from life to the motion of planets possible. The way energy interacts with matter is governed by several fundamental principles. The first of these principles is the conservation of energy. This is one of the cornerstones of physics. Energy cannot be created or destroyed, only transformed from one form to another. If you heat a pot of water on a stove, the energy from the gas or electricity used to heat the stove is transferred to the water, causing its molecules to move faster, which we experience as an increase in temperature. The total energy in the system, the stove, the water, and the surroundings, remains the same, but it changes form. This conservation of energy principle is universal, meaning it holds true for everything, from a falling apple to the workings of a complex machine. Energy also behaves in a way that is inherently tied to the physical laws that govern the universe. For example, the second law of thermodynamics tells us that energy tends to spread out over time, a process called entropy. As energy spreads, it becomes less usable. In simpler terms, some of the energy gets lost as heat, which we cannot always use to do work. This is why no machine or process is perfectly efficient. If you've ever tried to charge your phone and noticed the heat coming from the charger or the phone itself, that's an example of energy being lost in the form of heat. Even though we see energy in action around us all the time, the idea of harnessing it in ways that break the usual limits of efficiency or even conservation has been an ongoing challenge. After all, if energy is never lost but can only change forms, how can we possibly think about creating something like infinite energy? Is it even possible to tap into the kind of energy that could truly break the cycle of conservation? To answer that, scientists have begun to think about energy on a much deeper level. We're talking about the fundamental building blocks of the universe, the interactions that shape particles and forces, and the very nature of space and time. Could the secret to unlocking infinite energy lie in understanding these deeper layers of the universe? That's where experiments like the ALPHA experiment at CERN come in, where scientists are studying the interactions of antimatter, one of the most mysterious and potentially powerful forms of energy we've yet discovered. But before we dive into the details of that experiment, let's take a moment to reflect on something. When was the last time you thought about how much energy goes into your daily life? From the food you eat to the car you drive, every action you take is driven by energy. In fact, most of what we do as humans is in some way about harnessing or transforming energy, and yet, for all the energy we use, we are constantly looking for new ways to source and store more of it. So what if there was a source that never runs out? Could that be the key to solving the energy crisis that has plagued humanity for so long? As we continue exploring these questions, remember that what we think of as energy is really just a way of describing the forces that make things happen. Whether we're talking about nuclear power, electricity, or the food we eat, all of it comes down to one thing. Energy is the key to everything in our universe. So let's dive deeper into how scientists are exploring the potential for a new kind of energy, one that could be as transformative as it is elusive. As we venture further into the question of infinite energy, it's essential to first look back at the history of energy and the limits that science has uncovered over time. From the earliest moments of human history, we have been driven by the desire to harness power. The way we view energy today is the product of centuries of discoveries, struggles, and breakthroughs, each one pushing the boundaries of what we once thought possible. But those boundaries weren't always about what we could achieve. They were about understanding the fundamental limitations of energy itself. The earliest humans understood energy in a very basic sense. They could feel the heat of a fire and see how it could cook food, provide warmth, and offer light. They recognized the power of the wind to move ships and the power of flowing water to turn wheels. These early forms of energy were practical, but there was no understanding of their underlying mechanics. People harnessed energy in various forms, but they couldn't explain how or why energy behaved the way it did. The idea that energy could be understood in a scientific sense was still centuries away. In ancient times, the Greeks made some of the first intellectual strides toward understanding energy, even though they didn't have the language or tools to explore the concept in depth. They spoke of force and motion, and early thinkers like Aristotle tried to explain why things moved and what made them stop. But it wasn't until the Renaissance, with the work of figures like Galileo Galilei and Isaac Newton, that energy began to be systematically studied. Newton's laws of motion laid the foundation for classical mechanics, helping to formalize the relationship between force, motion, and energy. In his world, energy could be understood in terms of mechanical work, something that could be calculated and measured. It was a significant leap forward, yet still, there were boundaries to this understanding. In the 19th century, as the Industrial Revolution took hold, energy took on new forms and new significance. The rise of steam engines powered by coal marked a critical point in history where the ability to harness energy directly influenced the development of modern civilization. The steam engine itself was a breakthrough in utilizing thermal energy to perform mechanical work, and it dramatically changed society. However, even as these technologies grew more advanced, there were still clear boundaries set by the limitations of the materials and processes involved. The efficiency of early engines, for example, was far from perfect. Much of the energy produced in these machines was lost as heat, and no matter how much innovation occurred, these engines couldn't break the laws of thermodynamics. The concept of thermodynamics, which began to take shape in the 19th century, would soon redefine our understanding of energy and impose boundaries that science would struggle to overcome. The first and second laws of thermodynamics set limits on what could be done with energy. The first law, the law of conservation of energy, established that energy could neither be created nor destroyed, only transformed. This meant that no matter how much energy you tried to harness, you couldn't create more energy from nothing. The second law, known as entropy, stated that in any energy transformation, some of the energy would always be lost in the form of heat, and that systems naturally tend towards disorder. This means that even the most efficient machines could never be perfect. They would always lose energy and move towards a state of greater entropy. These boundaries were powerful, and they shaped our understanding of energy for over a century. But the dream of breaking free from these constraints didn't die. It simply evolved. As the 20th century unfolded, the exploration of electricity, magnetism, and later nuclear energy began to stretch the boundaries of what we thought was possible. The advent of quantum mechanics, led by scientists like Max Planck and Albert Einstein, introduced the idea that energy might behave in ways that defied classical understanding. In the quantum world, energy could exist in discrete packets called quanta, and particles like electrons didn't follow the predictable, continuous rules that classical mechanics suggested. But even in this new world, energy's limits were still apparent. Quantum mechanics opened up new frontiers, but it also came with its own set of rules, ones that couldn't be bypassed. One of the most significant developments in the 20th century came with the discovery of nuclear energy. The realization that atoms contained enormous amounts of energy waiting to be unlocked led to both the potential for devastating weapons and a new source of power. The atom bomb, with its release of unfathomable energy from a tiny amount of matter, seemed to offer a glimpse into a new kind of power. Nuclear reactors too harnessed the power of the atom to generate energy. But even nuclear energy had its limitations. The risks, the costs, and the need for complex infrastructure meant that it was far from the perfect solution. And the question remained, could there be a way to harness energy on an even grander scale, perhaps from the very fabric of the universe itself? Despite the advances in nuclear power and quantum mechanics, energy has continued to be something that needs to be generated, converted, and stored, each process inherently losing some of the potential energy in the system. The laws of thermodynamics are still in effect, and even the most advanced technologies cannot bypass them. As much as we've advanced in our understanding and application of energy, we're still working within the confines of those laws, but that's not to say that these boundaries are absolute. The dream of infinite energy, while once seen as a fantasy, is now something that scientists are actively researching, albeit in ways that require a deep understanding of the universe's most fundamental principles. Which brings us to today. We're at a moment in history where the boundaries of energy are being tested once again. But this time the experiments are more sophisticated and the possibilities more profound. The work being done at CERN, particularly with the ALPHA experiment, is pushing the limits of what we understand about energy, matter, and antimatter. Scientists are exploring the behavior of antimatter, a substance that could hold the key to new, previously unimaginable forms of energy. But whether this will lead to the discovery of truly infinite energy remains to be seen. What we can say for certain is that the pursuit of energy has always been a quest for more power, more efficiency, more control, and it's a quest that's far from over. Before we dive into the groundbreaking work at CERN, let's pause for a moment. Have you ever wondered just how much energy is contained in the smallest thing around you? A grain of sand, a drop of water. How much energy is locked away in that tiny speck of matter? That's the kind of question that pushes us to look deeper into the forces that shape our universe. And as we do, we come closer to understanding whether that dream of infinite energy can become a reality. So if you're finding this journey interesting, don't forget to like and subscribe. Let's continue to explore the limits of energy and whether those limits are as fixed as we once thought. As we explore the quest for infinite energy, one fundamental question rises above all others. Is it possible? This is not just a theoretical question. It's a practical one that has been at the heart of scientific inquiry for centuries. The dream of infinite energy seems to defy the natural laws that govern the universe, and yet it continues to capture the imagination of scientists, engineers, and innovators around the world. But how do we even begin to approach the idea that energy could exist without limits? And what, if anything, in the world of modern physics might suggest that infinite energy isn't just a fantasy? At the core of the question lies a challenge to the very foundations of what we understand about energy and the laws of physics. For centuries, scientists have operated under the assumption that energy is finite. The first and second laws of thermodynamics, which govern the behavior of energy, set clear boundaries. The first law tells us that energy can neither be created nor destroyed, only transformed. The second law tells us that in any energy transformation, some of the energy will be lost as heat, resulting in a system's natural tendency toward disorder or entropy. These laws are well established and have been confirmed through countless experiments and observations. They seem to create a wall that nothing can cross, a barrier that prevents the possibility of infinite energy from becoming a reality. But what if that wall wasn't as solid as it seemed? What if, in the deepest reaches of the universe, there are phenomena that don't follow these rules in the way we expect? This is where the idea of breaking the barrier of infinite energy begins to take shape. The possibility that there may be sources of energy in the universe that do not conform to our traditional understanding of thermodynamics is something that has intrigued scientists for years. And while we haven't yet found definitive proof that infinite energy is possible, there are certain theories and experiments that suggest it may not be entirely out of reach. One of the key areas where scientists are breaking barriers in energy research is in the study of antimatter. Antimatter, as you might know, is the opposite of regular matter. For every particle of matter, there is a corresponding antiparticle of antimatter with opposite charge. When matter and antimatter meet, they annihilate each other, releasing a tremendous amount of energy in the process. In fact, the energy released during this annihilation is far greater than what we get from most conventional sources of energy, such as fossil fuels or nuclear power. The annihilation of just 1 gram of antimatter could produce an amount of energy equivalent to the explosion of several kilotons of TNT. This raises an exciting question. Could we somehow harness this energy? If we could create antimatter and control its interaction with matter, could we unlock a source of energy that is orders of magnitude more powerful than anything we've ever known? Theoretically, this could provide an answer to the question of infinite energy, or at least a source of energy so vast that it would seem limitless. However, there's a catch. Creating and controlling antimatter is no easy feat. It's one of the most difficult and expensive challenges in modern physics. antimatter doesn't exist naturally in significant quantities in our universe. In fact, for every bit of antimatter that exists, there is an equal amount of matter, and the two annihilate each other upon contact. This means that creating antimatter requires vast amounts of energy, far more than we can currently produce. Additionally, storing antimatter is an enormous challenge because it can't touch regular matter without annihilating itself. Researchers at CERN, the European Organisation for Nuclear Research, have been working on creating and trapping small amounts of antimatter, but the process is slow, costly and inefficient. At this point, we're still far from being able to harness antimatter for practical energy production. That said, the possibility of antimatter-based energy remains a tantalizing prospect. Theoretically, if we could find a way to create and store antimatter efficiently, we might be able to tap into an energy source that defies the conventional limitations we've placed on energy production. Some even argue that antimatter could be a key ingredient in the development of advanced propulsion systems for space travel, potentially making interstellar travel a reality. But before we can even think about using antimatter as a practical source of energy, there are still major hurdles to overcome. So, is infinite energy possible? While the idea still seems far-fetched, the pursuit of antimatter and other theoretical sources of energy suggests that we may be closer than we think to breaking the barriers that have traditionally defined what is possible. At the very least, the research into these exotic forms of energy is pushing the limits of what we know, challenging the very laws of thermodynamics, and expanding our understanding of what might be achievable. In the next phase of our exploration, we'll take a closer look at how the ALPHA experiment at CERN is helping to unlock the mysteries of antimatter. This groundbreaking experiment is providing new insights into the behaviour of antimatter, and while it may not lead to infinite energy in the immediate future, it's helping to lay the groundwork for future advancements in energy production. The pursuit of infinite energy, though elusive, is one of the most exciting frontiers of modern science, and as researchers continue to push the boundaries of what we know, the dream of harnessing limitless power remains very much alive. Before we dive into the specifics of the ALPHA experiment, take a moment to consider this. If infinite energy were possible, how would it change the world? Imagine a future where energy isn't something we have to worry about, where the limitations that currently govern our civilization no longer apply. What could we achieve if we could tap into the vast reservoirs of energy hidden in the fabric of the universe? As we continue to explore the possibilities, I encourage you to think about how far we've come in our understanding of energy. The journey is far from over, and the answers we're seeking may be just around the corner. If you're enjoying this exploration, don't forget to like and subscribe, and let's keep pushing the boundaries together. The laws of thermodynamics are among the most fundamental principles in all of science. They govern the behaviour of energy, heat and work, and their implications stretch across everything from the smallest particles to the largest systems in the universe. Understanding these laws is crucial when exploring the limits of energy and whether something like infinite energy is even possible. They represent the boundaries of what we can achieve with energy, and any attempt to break those boundaries, whether through the dream of infinite energy or other ambitious pursuits, must contend with these laws. At the heart of thermodynamics are four fundamental laws, each one governing a different aspect of energy. These laws are not just theoretical, they are the bedrock of our understanding of the physical world. They have been tested and verified over and over again in experiments, and they dictate much of how energy behaves in the universe. The first law of thermodynamics, also known as the law of energy conservation, states that energy cannot be created or destroyed. It can only be transformed from one form to another. This is a simple, yet profound principle. If you think about the energy that powers your car, for example, it starts as chemical energy stored in gasoline. When the gasoline is burned in the engine, the chemical energy is converted into mechanical energy that moves the car, and also into heat energy that makes the engine warm. Even if energy changes form in various ways, the total amount of energy in the system remains constant. This law tells us that we cannot create energy from nothing, and we cannot destroy it once it exists. While the first law may sound straightforward, its implications are vast. It means that all of the energy in the universe has always existed in some form. The energy we use today, from the electricity powering our homes to the food we eat, is simply energy that has been transformed over time. But it also means that theoretically there is no new energy to tap into. If we could find a way to generate infinite energy, it would have to be based on some form of energy transformation, not creation from nothing. That's one of the key challenges in the search for infinite energy. No matter how much energy we gather, it will always be subject to this basic law of conservation. The second law of thermodynamics is just as important, and in many ways it presents an even more profound constraint. This law states that the total entropy, or disorder, of a system will always increase over time. In simple terms, entropy refers to the spread of energy and matter within a system. The second law suggests that energy will naturally disperse and become less useful. When energy is transferred or transformed, some of it becomes less ordered and more difficult to harness for productive work. This is why no machine or process can be perfectly efficient. When you burn gasoline in your car, only a portion of the energy goes into moving the car forward. The rest is lost as heat, raising the temperature of the engine and the surrounding air. The second law of thermodynamics is what gives rise to the phenomenon known as waste energy. This waste heat is not just a byproduct, it's an inevitable part of any energy conversion. The second law effectively places a limit on how efficiently we can use energy, and makes the idea of infinite energy seem impossible. If energy inevitably becomes more dispersed and less useful over time, how could we ever hope to accumulate an unlimited supply of it? The third law of thermodynamics brings us to a more subtle concept. It tells us that as the temperature of a system approaches absolute zero, the entropy of the system also approaches a minimum. In practical terms, this means that it's impossible to reach absolute zero. There is always some amount of energy or disorder present in any system. This law is often less intuitive, but it reinforces the idea that there are fundamental limits to how much we can reduce energy or disorder in a system. And finally, the fourth law of thermodynamics, also known as the zeroth law, is perhaps the simplest, but it forms the foundation for much of what we understand about temperature. It states that if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. In other words, heat flows from hot objects to cold ones until equilibrium is reached. This law is what underpins our entire concept of temperature and how heat energy behaves. Together, these laws form a framework that governs everything we know about energy. They tell us that energy cannot be created from nothing, that it inevitably becomes less usable over time, and that there are fundamental limits to how much we can control it. For anyone pursuing the idea of infinite energy, these laws present a significant challenge. How can we create energy without breaking the law of conservation? How can we harness energy without increasing entropy? The search for answers to these questions has driven scientists to explore some of the most exotic and fascinating corners of physics, and it's here that the possibilities for breakthrough innovations begin to emerge. But while these laws may seem like restrictions, they don't necessarily mean that the dream of infinite energy is completely out of reach. After all, science has a history of pushing the boundaries of what seemed impossible. For centuries, humans believed that flight was impossible, yet we now travel by air as a matter of course. The laws of thermodynamics certainly set limits, but they also provide a foundation for understanding the very forces we are working with. In this sense, they are both the rules that constrain us, and the rules that enable us to explore new ways of harnessing energy more efficiently. As we look at current advancements in energy research, particularly those happening at CERN with the ALPHA experiment, these laws provide context for understanding the challenges scientists are facing. The study of antimatter, for example, directly confronts the laws of thermodynamics. If antimatter can be harnessed as a form of energy, it would require overcoming significant obstacles. The energy released in antimatter annihilation is incredibly potent. but controlling and storing antimatter in a stable way presents a challenge far beyond the reach of current technology. That said, these challenges are not necessarily barriers to progress, they are problems to be solved. As we continue to explore the deepest mysteries of the universe, we may one day find new ways to work within the constraints of thermodynamics, or perhaps even discover phenomena that allow us to push those boundaries in ways we never imagined. The pursuit of infinite energy is far from over, and as our understanding of energy and the laws that govern it deepens, we get one step closer to breaking the rules in new, groundbreaking ways. As we continue to explore these possibilities, I encourage you to think about how these laws affect the everyday energy we rely on. Whether you're turning on a light, heating your home, or charging your phone, thermodynamics plays a role in how that energy behaves. And yet the pursuit of more efficient, more sustainable energy sources is a pursuit that stretches beyond what we know right now. The answers may lie in the unexplored corners of science, and who knows, perhaps we'll find ways to transcend these limits in ways we can't yet fully comprehend. If this discussion is sparking your curiosity, be sure to like and subscribe as we dive deeper into how these laws apply to the research being done at CERN. What happens when we push against the boundaries of these laws, and how far can science take us before we reach the true limit of what's possible? CERN, the European Organisation for Nuclear Research, stands as one of the most iconic research facilities in the world, a place where some of the deepest mysteries of the universe are being unravelled. Situated near Geneva, Switzerland, CERN is home to the largest particle accelerator ever built, the Large Hadron Collider, or LHC. The LHC isn't just a marvel of engineering, it's a gateway to understanding the fundamental building blocks of nature. At CERN, scientists aren't just looking at the universe from the outside, they're delving into its very core, exploring the particles and forces that shape everything we know. The work being done at CERN is more than just curiosity-driven science. It's a search for answers to the deepest questions about the fabric of reality itself. CERN was founded in 1954 with the goal of advancing knowledge about the smallest particles in nature. It has since grown into a global hub for physics research, drawing scientists and researchers from all over the world. The experiments conducted at CERN are pushing the limits of our understanding of the universe, from the origins of matter to the behaviour of antimatter, and even the fundamental forces that govern the interactions between particles. The discoveries made at CERN have the potential to revolutionise everything from technology to our fundamental understanding of physics. At the heart of CERN's research is the LHC, a particle accelerator that is both enormous and powerful. The LHC is a 17-mile-long ring buried deep underground, where particles are accelerated to nearly the speed of light before being collided at extremely high energies. These collisions recreate conditions that existed just moments after the Big Bang, allowing scientists to observe particle interactions in ways that are impossible to do under normal conditions. The energy levels in these collisions are so high that they can generate exotic particles that don't normally exist in our everyday world. These high-energy collisions also provide insights into the forces that govern the universe at the most fundamental level. One of the most famous discoveries at CERN was the detection of the Higgs boson in 2012. The Higgs boson, often referred to as the God particle, is a fundamental particle that was predicted by the standard model of particle physics, but had never been directly observed. Its discovery was a milestone in our understanding of the universe, confirming the mechanism by which particles acquire mass. The Higgs boson's discovery validated much of the theoretical framework that underpins particle physics, and provided a deeper understanding of how the universe works at the most basic level. But CERN's research goes far beyond just the Higgs boson. At CERN, scientists are exploring the nature of dark matter, a mysterious substance that makes up most of the matter in the universe, but remains invisible to traditional detection methods. They're investigating the properties of antimatter, which could hold the key to understanding new forms of energy. And they're also studying the behavior of quarks, leptons, and other fundamental particles that make up all the matter around us. Each experiment at CERN uncovers more about how the universe came to be and what it's made of. And each discovery opens up new questions, pushing the boundaries of what we know and driving us closer to understanding the true nature of reality. One of the most exciting aspects of CERN's research is the exploration of antimatter. Antimatter is the opposite of regular matter, and when matter and antimatter come into contact, they annihilate each other, releasing an enormous amount of energy. This process is so efficient that just a small amount of antimatter could potentially provide an immense amount of energy. However, antimatter is incredibly difficult to create and store. In fact, the amount of antimatter produced in experiments at CERN is so small that it's almost impossible to see without specialized equipment. But by studying antimatter and its properties, scientists are laying the groundwork for future energy breakthroughs that could change the way we think about power and energy production. At CERN, the ALPHA experiment is dedicated to studying antimatter in great detail. The ALPHA experiment focuses on creating and trapping antihydrogen, the antimatter counterpart to regular hydrogen. By studying antihydrogen, scientists hope to answer some fundamental questions about the universe. For instance, why is there so much more matter than antimatter in the universe? According to current theories, the Big Bang should have produced equal amounts of matter and antimatter, but we see far more matter around us. Understanding why this imbalance exists could provide profound insights into the early history of the universe and the nature of the forces that govern it. The ALPHA experiment at CERN is just one example of how the research being done at the facility is pushing the boundaries of what we know. By creating and studying antimatter, scientists are gaining new insights into the fundamental nature of energy. The potential applications of antimatter are vast, from powering spacecraft to providing a nearly limitless source of energy. But there's still much to learn, and much work to be done before we can begin to harness antimatter in practical ways. The research at CERN is far from complete, and as new technologies and experimental techniques continue to evolve, the potential for groundbreaking discoveries only grows. The study of antimatter at CERN is not just about energy, however. It's also about understanding the fundamental forces that govern the universe. At the subatomic level, particles interact through four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Each of these forces plays a crucial role in shaping the behavior of particles and the structure of matter. The research being done at CERN is helping scientists uncover the mysteries of these forces and how they interact with one another. As we continue to study the forces of nature, one of the most exciting questions is whether there are more forces than the four we currently know about. Could there be additional forces that are hidden from us? Could there be ways to unify the forces into a single framework, as physicists have long hoped? These are questions that have yet to be answered, but CERN is at the forefront of the search for new answers. By examining the interactions between particles at extremely high energies, scientists hope to uncover clues that could lead to the discovery of new forces and new laws of physics. The research at CERN also has the potential to revolutionize technology in ways we can't yet imagine. The discoveries made in particle physics often lead to technological advancements that have a profound impact on our everyday lives. For example, the invention of the World Wide Web was the result of a need to share data between researchers at CERN. The technologies developed for particle physics experiments have led to advancements in fields as diverse as medicine, computing, and material science. As our understanding of the universe deepens, the technologies we develop to study it are likely to have far-reaching effects on the way we live and work. CERN is more than just a research facility. It's a symbol of humanity's drive to explore the unknown. The questions being asked at CERN are some of the most profound and fundamental questions about the nature of reality. Can we understand the origin of the universe? Can we unlock the secrets of antimatter and energy? Can we find new ways to harness the forces of nature? These are questions that challenge our very understanding of existence, and the research at CERN is helping to answer them. The discoveries made there have the potential to change everything we know about the universe, from the smallest particles to the vast reaches of space. As we continue to explore these mysteries, let's take a moment to reflect on what we've learned so far. The research at CERN represents the cutting edge of human knowledge, and it's pushing the boundaries of what we thought was possible. The potential to unlock new sources of energy, uncover new forces, and deepen our understanding of the universe is within our grasp. But there's still much to discover, and as we continue on this journey, we'll see how the groundbreaking work at CERN might one day lead to the answers we've been searching for. The ALPHA experiment at CERN is a cutting-edge endeavour that focuses on one of the most mysterious and fascinating substances in the universe: antimatter. Antimatter is often portrayed in science fiction as an almost magical substance, but in reality it's very real, and it holds the potential to revolutionise everything from energy production to our understanding of the universe itself. The ALPHA experiment is helping to unlock the secrets of antimatter, and in doing so it is giving us a glimpse into a new frontier of science. To understand why antimatter is so important, it helps to first grasp what it is. Matter, as we know it, is made up of atoms, which consist of protons, neutrons, and electrons. These are the building blocks of everything in the universe, from the air we breathe to the stars in the sky. Antimatter, on the other hand, is the opposite of matter. Every particle of matter has a corresponding antiparticle in antimatter with the opposite charge. For example, the antiparticle of a proton is called an antiproton, and the antiparticle of an electron is called a positron. When matter and antimatter come into contact, they annihilate each other, releasing an enormous amount of energy in the process. This is one of the most fascinating properties of antimatter. It's incredibly energy dense. Just a small amount of antimatter could produce vast amounts of energy. In fact, the energy released when matter and antimatter annihilate is far greater than the energy released in conventional nuclear reactions. This means that antimatter has the potential to be a nearly limitless source of energy, but there's a catch. Creating and containing antimatter is incredibly difficult. The ALPHA experiment at CERN is dedicated to studying antimatter, specifically antihydrogen, which is the antimatter counterpart to hydrogen. Hydrogen is the simplest and most abundant element in the universe, made up of a single proton and a single electron. Antihydrogen is made up of an antiproton and a positron, and it behaves in many ways like regular hydrogen, but with the opposite charge. By creating antihydrogen and studying its properties, scientists hope to answer some of the biggest questions in physics, such as why there is so much more matter than antimatter in the universe, and whether antimatter could be harnessed as a viable energy source. The challenge in studying antimatter is that it's incredibly rare in nature. For every particle of matter, there is a corresponding antiparticle of antimatter, but they annihilate each other upon contact. This means that antimatter is virtually impossible to find in significant quantities in the universe. The ALPHA experiment at CERN is working to create small amounts of antihydrogen by accelerating and colliding particles in a particle accelerator. Once produced, the antihydrogen atoms are trapped using magnetic fields and studied to better understand their behaviour. One of the key goals of the ALPHA experiment is to investigate the properties of antihydrogen, particularly how it behaves under the influence of gravity. One of the big mysteries in physics is why matter and antimatter behave the way they do. If matter and antimatter are created equally in the universe, why is the universe dominated by matter, with almost no antimatter present? This is known as the matter-antimatter asymmetry problem, and it's one of the most profound questions in modern physics. Understanding how antimatter interacts with gravity could help answer this question and provide new insights into the very nature of the universe. The ALPHA experiment is also studying the fundamental interactions of antimatter. For example, scientists are investigating whether antimatter behaves the same way as matter in terms of fundamental forces such as electromagnetism. If antimatter behaves differently from matter in some way, it could open the door to new physics beyond our current understanding. On the other hand, if antimatter behaves in exactly the same way as matter, it would provide strong evidence for the idea that the laws of physics are symmetric, meaning that they work the same way for both matter and antimatter. Another area of research in the ALPHA experiment is the possibility of creating antimatter-based technologies. If we could create and store enough antimatter, it could potentially be used as a source of energy or even as a propulsion system for space travel. The energy released when antimatter and matter annihilate is so intense that even small amounts of antimatter could generate enormous amounts of power. If we could figure out a way to produce antimatter efficiently and store it safely, it could revolutionize everything from energy production to space exploration. However, there are significant challenges in harnessing antimatter for practical use. For one thing, the amount of antimatter produced at CERN is minuscule. The ALPHA experiment has managed to trap only a few hundred atoms of antihydrogen at a time, and creating these tiny amounts of antimatter requires a tremendous amount of energy. In fact, the energy required to create antimatter far exceeds the energy we can currently extract from it. But this doesn't mean that the potential isn't there. Scientists are hopeful that with advances in technology, we may one day be able to create antimatter on a larger scale and find ways to harness its energy. The ALPHA experiment is still in its early stages, but it's already making significant progress. By studying antimatter in more detail, scientists are not only learning more about this elusive substance, but are also developing the tools and techniques that could one day make antimatter a practical resource. The discoveries being made at CERN are laying the groundwork for future advancements in energy production, propulsion systems, and our understanding of the universe itself. For now, the work at CERN remains at the frontier of science. The ALPHA experiment is pushing the boundaries of what we know about antimatter, and it's providing a glimpse into a future where antimatter could become an integral part of our world. While we're still a long way from harnessing antimatter for practical use, the progress being made at CERN is opening up new possibilities for energy, space exploration, and fundamental physics. As we continue to explore the mysteries of antimatter, we're left with more questions than answers. What are the true properties of antimatter? How can we create and store it in meaningful quantities? And perhaps most importantly, can antimatter provide the key to unlocking new forms of energy? These questions are at the heart of the ALPHA experiment, and as scientists continue their work, we may one day find the answers that could change everything we know about energy in the universe. Antimatter is one of the most intriguing and elusive concepts in modern physics, often bringing to mind images of futuristic technology and science fiction stories. But despite its somewhat fantastical reputation, antimatter is a very real part of the universe. It exists, albeit in very small amounts, and its properties could revolutionize our understanding of everything from energy production to the fundamental structure of the universe itself. To understand antimatter, we must first look at the matter that makes up everything around us. Matter, as we know it, is made up of atoms, and these atoms are in turn made up of particles, protons, neutrons, and electrons. The protons and neutrons reside in the atom's nucleus, while the electrons orbit around the nucleus. These particles carry specific charges. Protons have a positive charge, electrons have a negative charge, and neutrons have no charge at all. The way these particles interact with one another is governed by the fundamental forces of nature, such as electromagnetism, which causes opposite charges to attract and like charges to repel. Now, antimatter is essentially the opposite of this. For every particle of matter, there is a corresponding antiparticle in antimatter. These antiparticles have the same mass as their matter counterparts, but opposite electric charges. For example, the antiparticle of a proton is called an antiproton, and it has a negative charge instead of a positive charge. Similarly, the antiparticle of an electron is called a positron, and it has a positive charge instead of a negative charge. When matter and antimatter meet, they annihilate each other, releasing a tremendous amount of energy. This process is incredibly efficient. meaning that even a small amount of antimatter could release an enormous amount of energy. For example, if you had just 1 gram of antimatter and it came into contact with 1 gram of matter, the amount of energy released would be equivalent to the explosion of several kilotons of TNT. This is why antimatter is so interesting to scientists. It holds the potential to be an incredibly dense and powerful source of energy. But while the potential of antimatter is vast, it's also extremely difficult to produce and contain. Antimatter doesn't naturally occur in large amounts in our universe. In fact, when the universe was created in the Big Bang, equal amounts of matter and antimatter should have been produced. However, for reasons that scientists still don't fully understand, the universe is made almost entirely of matter, with very little antimatter to be found. This asymmetry between matter and antimatter is one of the most profound mysteries in physics. Why did the universe end up dominated by matter, and what happened to all the antimatter? The answer to this question is still unclear, but one thing is certain: antimatter is incredibly rare. It's so rare that in fact it's nearly impossible to find it in nature. For example, when high-energy cosmic rays strike the Earth's atmosphere, they can sometimes produce antimatter particles, but these particles are quickly annihilated when they come into contact with matter. This makes antimatter nearly impossible to study in its natural state. At CERN, scientists are working to create and study small amounts of antimatter in the laboratory. One of the most important experiments in this area is the ALPHA experiment, which focuses on producing antihydrogen, the antimatter counterpart to hydrogen. By accelerating particles to high energies and then allowing them to collide, scientists can create antihydrogen atoms and trap them for study. These atoms are incredibly fragile, and the amount of antimatter produced in these experiments is minuscule, much smaller than what would be required to harness it as a practical energy source. Nonetheless, the ALPHA experiment is making significant strides in understanding the properties of antimatter and its potential uses. In addition to its potential as an energy source, antimatter also holds the key to answering some of the most fundamental questions in physics. For example, the study of antimatter could help scientists understand why the universe is made of matter rather than antimatter. This is a question that goes back to the earliest moments of the universe and touches on some of the deepest mysteries in cosmology. If matter and antimatter were created in equal amounts at the time of the Big Bang, why did the antimatter seem to disappear? Could it be that some unknown force or process tipped the balance in favour of matter, leading to the universe we observe today? By studying the interactions between matter and antimatter, scientists hope to uncover new information about the laws of physics and how they govern the universe. If antimatter behaves differently from matter in some way, it could point to new forces or new principles that govern the interactions between particles. Conversely, if antimatter behaves in exactly the same way as matter, it could provide strong evidence for the idea that the laws of physics are symmetric, meaning that they work the same way for both matter and antimatter. Another exciting possibility is that antimatter could be used as a source of energy. If we could find a way to create and store enough antimatter, the energy released when it annihilates with matter could be used to power machines, spacecraft, or even entire cities. This could provide an energy source far more efficient than anything we currently have. However, the challenges of creating and storing antimatter are immense. The ALPHA experiment has successfully trapped small amounts of antihydrogen, but the amount produced is still far too small to be practically useful. In addition, antimatter must be stored in a way that prevents it from coming into contact with matter, which would cause it to annihilate instantly. This requires the development of extremely advanced technology, including sophisticated magnetic fields and vacuum systems to keep antimatter isolated. Despite these challenges, the potential of antimatter remains tantalizing. If scientists can find a way to produce and store enough antimatter, it could revolutionize everything from energy production to space travel. Antimatter propulsion, for example, could enable spacecraft to travel vast distances in a fraction of the time it would take with conventional propulsion methods. This is one of the reasons why antimatter is often discussed in the context of future space exploration. Its energy density is so high that it could make interstellar travel a reality. But we're still far from that point. The current methods of creating antimatter are slow and energy intensive, and the quantities produced are incredibly small. However, as technology advances and as experiments like ALPHA continue to push the boundaries of what we can do with antimatter, we may one day find ourselves on the cusp of unlocking one of the most powerful forms of energy known to science. For now, the study of antimatter remains an exciting and challenging field of research. It holds the promise of new discoveries that could transform our understanding of the universe and potentially change the way we harness energy. But for now, scientists are focused on one step at a time, carefully studying the properties of antimatter and continuing to refine the methods for creating and trapping it. With each new discovery, we get a little closer to understanding the true nature of antimatter, and with it, the potential to unlock an entirely new chapter in the story of energy and the universe. When antimatter meets matter, it's not a simple encounter. It's a violent, energy-releasing collision that transforms both substances into pure energy. This is the essence of what makes antimatter so fascinating and potentially so powerful. The sheer amount of energy that is released when the two meet. The process is called annihilation, and it's one of the most efficient energy releases known to physics. When a particle of matter comes into contact with its corresponding antiparticle, they destroy each other. For example, when a proton and an antiproton collide, they annihilate each other, releasing energy in the form of gamma rays, high-energy electromagnetic radiation. This is a process where the total mass of the two particles is converted entirely into energy, in accordance with Einstein's famous equation E equals mc squared. This equation tells us that mass and energy are interchangeable, and it's this principle that underpins the enormous energy potential of matter, antimatter annihilation. The key to understanding why this process releases so much energy lies in the relationship between mass and energy. The mass of a single particle, like a proton or an electron, is incredibly small. But when you consider the annihilation of even just a tiny amount of matter with antimatter, the resulting energy release is far greater than that of any conventional energy source. To put it into perspective, the annihilation of just 1 gram of antimatter with 1 gram of matter would release an amount of energy equivalent to the explosion of about 43 kilotons of TNT. This is a staggering amount of energy, especially when you consider the tiny size of the particles involved. This makes antimatter an extremely efficient energy source. While traditional energy sources like fossil fuels, nuclear power, or even solar energy release energy through chemical reactions or the transformation of energy between different forms, antimatter annihilation produces energy in its purest form. The potential applications for this kind of energy are vast, from space travel to possibly providing clean, near-limitless power. The problem, however, is that antimatter is incredibly difficult and expensive to produce, and current technologies can only create minuscule amounts of it. At CERN, scientists are studying the process of matter-antimatter annihilation in great detail. The ALPHA experiment, in particular, is focused on producing antihydrogen, which is the antimatter counterpart to hydrogen. By creating antihydrogen and observing how it interacts with regular matter, scientists are learning more about how antimatter behaves and how it might be harnessed for energy. While the amounts of antimatter produced at CERN are tiny, the research is paving the way for future breakthroughs that could one day make antimatter a practical source of energy. But creating and storing antimatter is no small feat. The first challenge is producing enough antimatter to make it useful. While antimatter can be created in particle accelerators, like the Large Hadron Collider, LHC, the process is highly inefficient. For every particle of antimatter produced, a far greater amount of energy is required. In fact, the energy required to create antimatter currently far exceeds the energy that could be obtained from its annihilation. This makes antimatter an energy-intensive process, and right now it's not a practical solution for large-scale energy production. In addition to production, the storage of antimatter presents another massive challenge. Since antimatter annihilates upon contact with matter, it can't be stored in regular containers. To prevent this from happening, antimatter must be contained using magnetic fields in a vacuum. This is precisely what the scientists at CERN are doing in the ALPHA experiment. By using strong magnetic fields, they are able to trap tiny amounts of antihydrogen for short periods of time. However, the amounts of antimatter that can be produced and trapped in this way are still minuscule, far too small to be used as an energy source at this point. Despite these challenges, the potential benefits of antimatter as an energy source are enormous. If we could find a way to produce antimatter more efficiently and store it safely, it could be a game changer for energy production. The energy released by antimatter annihilation is so vast that even small amounts could power entire cities, spacecraft, or other technologies that rely on large amounts of energy. The possibilities are virtually limitless. But it's important to remember that antimatter is not just an energy source, it's also a tool for understanding the universe. The study of antimatter can provide insights into some of the most fundamental questions in physics. For example, scientists are still trying to understand why the universe is made mostly of matter rather than antimatter. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter, but we don't observe much antimatter in the universe today. This asymmetry is one of the greatest mysteries in cosmology, and studying antimatter might provide the key to unlocking the answer. Moreover, antimatter's potential extends beyond just energy production. In space exploration, antimatter propulsion is one of the most exciting theoretical concepts. If antimatter could be used as a propulsion system, spacecraft could potentially travel vast distances in a fraction of the time it would take using conventional methods. The energy density of antimatter is so high that even a small amount could provide the thrust needed for interstellar travel, making missions to distant planets or even other star systems a possibility. However, we're still a long way from being able to harness antimatter for these purposes. Right now, the quantities of antimatter that can be produced are too small to make a meaningful impact. In addition, the technologies needed to store and control antimatter are still in their infancy. But as research progresses, and as new technologies are developed, the dream of using antimatter for energy or space travel could one day become a reality. For now, the research into antimatter continues to be one of the most fascinating areas of physics. Every new experiment, every new discovery brings us one step closer to understanding how antimatter works and how it might one day be used. Whether it's in the form of energy production, propulsion systems, or a deeper understanding of the universe's origins, the possibilities are truly exciting. As we move forward, it's important to keep in mind the sheer scale of what we're attempting to achieve. We're not just looking for new ways to produce energy, we're seeking to unlock one of the most fundamental and powerful forces in the universe. And as we continue to push the boundaries of science, who knows what we'll discover about antimatter and the potential it holds for shaping the future of humanity. The search for balance between matter and antimatter is one of the most profound and enduring questions in the field of physics. The mystery lies at the very heart of the universe's existence. According to the laws of physics, the Big Bang should have created equal amounts of matter and antimatter. But as we look around us today, we see a universe dominated by matter, with very little antimatter to be found. This imbalance between matter and antimatter is a central puzzle that scientists are working tirelessly to solve, and its resolution could change our understanding of everything from the origins of the universe to the possibility of new forms of energy. To appreciate why this search for balance is so important, let's first look at the relationship between matter and antimatter. Matter, as we know it, is made up of atoms, which consist of particles like protons, neutrons, and electrons. These particles have positive or negative charges, and they interact according to the fundamental forces of nature, such as electromagnetism and gravity. Antimatter is essentially the opposite of matter. For every particle of matter, there is a corresponding antiparticle in antimatter which has the opposite charge. For example, the antiparticle of a proton is the antiproton, and the antiparticle of an electron is the positron. When matter and antimatter come into contact, they annihilate each other in a process that releases an enormous amount of energy. This annihilation is incredibly efficient, with nearly all of the mass being converted into energy, typically in the form of high-energy gamma rays. Because of this, antimatter is not only a fascinating subject for study, but it also holds enormous potential as a source of energy. If we could find a way to produce and store antimatter, it could revolutionize our approach to energy production, offering a potential energy source that is far more powerful than anything we currently have. However, the question that continues to elude scientists is why there seems to be so much more matter than antimatter in the universe. According to the standard model of particle physics, matter and antimatter should have been created in equal amounts during the Big Bang. But if this was the case, why do we observe almost no antimatter in the universe today? Instead, the universe is composed almost entirely of matter. This asymmetry between matter and antimatter is known as the matter-antimatter imbalance, and it's one of the most significant unsolved problems in modern physics. Scientists have proposed several theories to explain this imbalance. One possibility is that there was a slight asymmetry in the way that matter and antimatter were produced in the early universe. If a tiny excess of matter was created over antimatter, then as the universe cooled and expanded, matter would have prevailed, leaving behind a small amount of antimatter that was annihilated with the matter. This excess of matter over antimatter could have been the seed for the universe as we know it today. But this theory is far from proven, and it leaves many questions unanswered. If the Big Bang produced equal amounts of matter and antimatter, what happened to the antimatter? Why did it disappear almost entirely, leaving only traces behind? The answer to this question could hold the key to understanding not just the origins of the universe, but also the fundamental forces that govern the behavior of particles. To explore this imbalance, scientists are conducting experiments in particle accelerators, such as those at CERN. The ALPHA experiment, for example, is specifically focused on studying antimatter. By producing and trapping tiny amounts of antihydrogen, the antimatter counterpart of hydrogen, scientists are able to study the properties of antimatter in great detail. One of the primary goals of the ALPHA experiment is to investigate whether antimatter behaves in the same way as matter, particularly when it comes to the fundamental forces of nature such as gravity. If antimatter behaves differently from matter in some way, it could provide clues to understanding the matter-antimatter imbalance. For example, if antimatter reacts differently to gravity than matter, it could explain why we see more matter than antimatter in the universe. On the other hand, if antimatter behaves in the same way as matter, it would suggest that the laws of physics are symmetric, and that the imbalance must have arisen from some other unknown factor. In addition to the ALPHA experiment, other experiments at CERN and around the world are studying the interactions between matter and antimatter. One of the key areas of research is how antimatter responds to electromagnetic forces. Since antimatter has opposite charges to matter, it should, in theory, behave similarly when exposed to magnetic and electric fields. However, scientists have yet to confirm whether antimatter behaves exactly the same as matter in this respect, and this could provide important insights into the mystery of the matter-antimatter imbalance. The search for balance is not limited to just understanding the origin of the universe. It also has important implications for the future of technology and energy. If we can better understand antimatter and learn how to control it, we could unlock new sources of energy that are far more efficient than anything we currently use. Antimatter's energy release, when matter and antimatter annihilate, is so intense that even small amounts could produce vast amounts of power. This makes antimatter a potential candidate for advanced propulsion systems in space travel. potentially allowing us to travel across the cosmos at speeds previously thought impossible. The energy density of antimatter is so high that it could be the key to long-distance space exploration, enabling humanity to venture beyond the confines of our solar system. However, there are many obstacles to overcome before antimatter can become a practical energy source or propulsion system. Producing antimatter is incredibly difficult and requires immense amounts of energy. The ALPHA experiment, for example, has managed to create small amounts of antihydrogen, but the amount of antimatter produced is still tiny. Moreover, antimatter must be stored in a way that prevents it from coming into contact with matter, which would cause it to annihilate. This requires the development of advanced magnetic and vacuum technologies, and we are still a long way from being able to store and use antimatter on a large scale. Despite these challenges, the search for balance between matter and antimatter continues to be one of the most exciting frontiers in science. Understanding why there is more matter than antimatter in the universe is crucial to unlocking many of the fundamental mysteries of the cosmos. And as experiments like ALPHA continue to push the boundaries of our knowledge, we may one day find answers that not only explain the origin of the universe, but also open up new possibilities for energy and space exploration. As we continue to explore the mysteries of antimatter, one thing is clear: the search for balance is far from over. With each experiment, with each new discovery, we get closer to understanding one of the most profound questions in physics. And who knows? Perhaps in the not-too-distant future, we will have unlocked the secrets of antimatter and achieved the balance between matter and antimatter that will transform the future of science and technology. The energy of the future might very well be found in the most exotic substance known to science: antimatter. While antimatter might seem like something out of a science fiction novel, it is in fact a real phenomenon that scientists are now beginning to study in greater detail. The potential for antimatter to serve as a source of energy is enormous, but the challenges involved in harnessing it are just as vast. If we can find a way to produce and control antimatter efficiently, it could transform the way we think about energy production and energy consumption. To fully grasp the potential of antimatter as an energy source, it helps to understand just how much energy it contains. When antimatter and matter come into contact, they annihilate each other, releasing a tremendous amount of energy in the process. The annihilation of a single gram of antimatter with a single gram of matter would release an amount of energy equal to about 43 kilotons of TNT, far more than the energy released by any conventional fuel source. This makes antimatter an incredibly energy-dense material, one that could, in theory, provide a nearly limitless source of power. The reason antimatter is so powerful lies in the fact that it's a form of energy that doesn't just convert into heat or mechanical work, as most other energy sources do. Instead, when matter and antimatter annihilate, their entire mass is converted directly into energy, in accordance with Einstein's famous equation E equals mc squared. This makes antimatter an incredibly efficient energy source, capable of producing vastly more energy than conventional methods, like burning fossil fuels or even nuclear reactions. The only problem is that antimatter is extremely difficult to create and store. At present, the production of antimatter is a slow and energy-intensive process. Particle accelerators like the ones at CERN can produce tiny amounts of antimatter, but the process is highly inefficient. For every particle of antimatter created, far more energy is required than can be obtained from the annihilation of the antimatter itself. The energy required to produce antimatter far exceeds the energy we can currently extract from it. This makes antimatter impractical as an energy source with current technology. Yet, despite these challenges, antimatter is still seen as one of the most promising candidates for future energy production. If we could find a way to produce antimatter more efficiently and in larger quantities, we could unlock an energy source that is vastly more powerful than anything we have today. One of the most exciting possibilities is the use of antimatter in space travel. The energy density of antimatter is so high that it could be used to propel spacecraft at speeds much faster than current propulsion systems allow. If antimatter could be harnessed as a source of energy for propulsion, it could enable interstellar travel, taking us to distant planets and even other star systems. But before we can harness antimatter in practical ways, there are a number of significant obstacles that must be overcome. The first challenge is production. As mentioned earlier, producing antimatter in large quantities requires huge amounts of energy. Current methods of creating antimatter involve accelerating particles to high energies and then allowing them to collide, creating antimatter as a byproduct. However, only tiny amounts of antimatter are produced in these experiments, and the process is incredibly energy intensive. In fact, for every gram of antimatter created, an enormous amount of energy, thousands of times more than what can be extracted, is consumed in the process. The second major challenge is storage. Since antimatter annihilates upon contact with regular matter, it cannot be stored in ordinary containers. Instead, it must be trapped using magnetic fields and kept in a vacuum. This requires advanced technology, such as the techniques used in the ALPHA experiment at CERN, where scientists are able to trap small amounts of antihydrogen using strong magnetic fields. However, even with these techniques, the amounts of antimatter that can be produced and trapped are still minuscule. The technology needed to store and contain antimatter on a larger scale simply does not exist yet. Despite these challenges, there is significant progress being made in the field of antimatter research. The ALPHA experiment at CERN is one of the key efforts in this area, and it's providing scientists with new insights into how antimatter behaves and how it might one day be used. The ability to trap antihydrogen, the antimatter counterpart of hydrogen, for extended periods is a major breakthrough, and it's helping researchers learn more about the properties of antimatter and its interactions with matter. The goal is to eventually produce enough antimatter to make it useful for practical applications, such as energy production or space propulsion. There is also hope that future technological advancements could make the production and storage of antimatter more efficient. For example, new breakthroughs in particle accelerators, magnetic containment systems, and energy efficiency could dramatically reduce the amount of energy required to produce antimatter and increase the amount that can be stored. If such advancements are made, antimatter could one day become a viable energy source, providing a nearly limitless supply of power. The possibilities are staggering. Imagine a future where antimatter is used to power entire cities, or where spacecraft powered by antimatter engines travel to distant star systems. The energy potential of antimatter is so vast that it could transform everything from energy production to transportation to the very nature of space exploration. But to get there, we need to make significant advancements in the technology required to produce, store, and harness antimatter. This is a long-term goal, and it may take decades or even centuries before antimatter becomes a practical energy source. For now, the study of antimatter remains one of the most exciting and cutting-edge areas of physics. The breakthroughs being made at CERN and other research facilities are laying the groundwork for future advancements, and every new discovery brings us closer to understanding how antimatter works and how we might one day use it. While the road ahead is long and fraught with challenges, the potential rewards are immense. If we can unlock the secrets of antimatter and find a way to harness it, we could tap into a nearly unlimited source of energy, reshaping the future of our planet and our ability to explore the stars. In the meantime, the search continues. The future of energy may very well lie in the most exotic substance in the universe, and as scientists continue their work, they are moving us closer to the day when antimatter becomes a part of our everyday lives. The ALPHA experiment at CERN represents one of the most exciting and ambitious efforts in the field of antimatter research. It's a project that, at its core, aims to answer some of the most fundamental questions about the nature of matter and antimatter. By creating and trapping antihydrogen, the antimatter counterpart of hydrogen, the ALPHA experiment is pushing the boundaries of our understanding of the universe. However, while the potential of antimatter is immense, the challenges involved in studying it are equally significant. The road to breakthroughs in the alpha experiment is a long and difficult one, and it requires overcoming both technical hurdles and theoretical complexities. At the heart of the alpha experiment is the goal of creating and studying antihydrogen, which consists of an antiproton and a positron. This is no easy task. The production of antimatter requires extremely high energy collisions between particles, and the amount of antimatter produced in these collisions is incredibly small, typically on the order of a few hundred antihydrogen atoms at most. This creates an immediate challenge. How do you study something as elusive and fleeting as antimatter when it only exists for a fraction of a second? The first major breakthrough in the alpha experiment came with the development of a method for trapping antihydrogen. Since antimatter annihilates upon contact with regular matter, it can't simply be stored in a container. To study it, scientists must prevent it from interacting with matter. This is where magnetic fields come into play. By using a powerful magnetic trap, the alpha experiment is able to contain antihydrogen atoms in a vacuum, keeping them away from the walls of the trap and allowing researchers to study their properties. This magnetic trap uses a combination of electric and magnetic fields to keep antihydrogen suspended and isolated from the surrounding environment, preventing it from annihilating with matter. Creating and trapping antihydrogen is just the beginning, though. The real challenge lies in the precision required to study antimatter. Because antihydrogen is so unstable, it is incredibly difficult to observe directly. To study the properties of antihydrogen, scientists need to measure its interactions with other particles and forces. One of the most important experiments in the Alpha project is to study how antihydrogen behaves under the influence of gravity. If antimatter behaves the same as matter in this regard, it would provide evidence that the fundamental laws of physics apply equally to both. However, if antimatter behaves differently, it could indicate that there are new forces at play, forces that we don't fully understand yet. In order to test how antimatter interacts with gravity, the Alpha experiment requires extreme precision in its measurements. The antihydrogen atoms need to be confined and observed with incredibly accurate instruments, and the interaction of antimatter with gravity needs to be measured with high sensitivity. This precision is difficult to achieve, given the tiny amounts of antimatter involved and the brief lifetimes of antihydrogen atoms. Each measurement needs to be repeated many times to ensure accuracy, and even the smallest error in the experimental setup could lead to skewed results. Another significant challenge in the Alpha experiment is the issue of energy efficiency. The process of creating antimatter requires vast amounts of energy. In fact, the amount of energy needed to produce antimatter far exceeds the energy that can be extracted from it in the form of annihilation. This means that, at present, antimatter is not a practical energy source. The production of antimatter is highly inefficient, and scientists are working on finding ways to improve this efficiency. For now, antimatter remains a fascinating subject of study, but it's not something we can yet use as a reliable source of power. The Alpha experiment also faces challenges in terms of the storage and handling of antimatter. While magnetic traps are used to isolate antihydrogen, these traps are delicate and can only hold the antimatter for a short time. The longer the antihydrogen can be contained, the more information scientists can gather about its properties. But even with the most advanced technology, there are limits to how long antimatter can be trapped. In the future, one of the goals of antimatter research will be to extend the amount of time that antimatter can be stored, which would provide more opportunities for experimentation and a better understanding of its behavior. Despite these significant challenges, the breakthroughs achieved by the Alpha experiment are nothing short of remarkable. The ability to trap antihydrogen for extended periods is a major step forward in antimatter research. This accomplishment has opened the door to a whole new realm of experiments, allowing scientists to test the properties of antimatter and its interactions with the fundamental forces of nature. These experiments are not just about the potential for new energy sources, they are also about deepening our understanding of the universe itself. By studying antimatter, we are testing the limits of the known laws of physics, and perhaps even finding evidence for new, unexplored principles. One of the most exciting aspects of the ALPHA experiment is its potential to help answer one of the biggest mysteries in physics, the matter-antimatter asymmetry. The Big Bang should have produced equal amounts of matter and antimatter, but today, the universe is almost entirely composed of matter, with very little antimatter to be found. Understanding why this imbalance exists is one of the most profound questions in cosmology, and the ALPHA experiment could provide the key to solving it. If scientists can determine whether antimatter behaves the same as matter, under the influence of gravity and other forces, they may gain new insights into why the universe is made of matter rather than antimatter. Moreover, the ALPHA experiment could lay the groundwork for future advancements in antimatter-based technologies. While we're still far from being able to use antimatter as a practical source of energy, the study of antimatter is paving the way for breakthroughs in propulsion systems, energy production, and even space exploration. The idea of using antimatter as a propulsion system for spacecraft is particularly exciting. The energy released when antimatter and matter annihilate is so powerful that it could enable spacecraft to travel vast distances at speeds much faster than conventional propulsion systems allow. This could make interstellar travel a reality, opening up new possibilities for humanity to explore the far reaches of the universe. In conclusion, the ALPHA experiment is at the forefront of one of the most exciting and challenging areas of research in modern physics. While there are still many obstacles to overcome, the breakthroughs achieved so far are laying the foundation for a deeper understanding of antimatter and its potential applications. As technology advances and our understanding of antimatter grows, the ALPHA experiment could help us unlock one of the most powerful energy sources in the universe, and potentially change the future of energy production, space exploration, and our understanding of the cosmos itself. The question of whether we could create infinite energy from antimatter is both tantalizing and daunting. The potential of antimatter as an energy source is staggering, but the challenges in producing, storing, and harnessing it make the idea of infinite energy seem distant. However, the concept itself is rooted in the fundamental nature of antimatter and its interactions with matter. If we could find a way to control antimatter efficiently, the energy released through annihilation could, in theory, provide an almost limitless supply of power. But before we can get too excited about antimatter's potential, it's essential to break down both its promise and its limitations. The energy released when antimatter comes into contact with matter is one of the most energy-efficient processes known to science. When a particle of matter collides with its corresponding antiparticle, the two annihilate each other, converting their mass into pure energy, as described by Einstein's famous equation, E equals mc squared. This is a process that is incredibly efficient compared to any other energy release mechanism. For example, a small amount of antimatter, just 1 gram, could theoretically release enough energy to destroy a large building. This is the kind of energy density that fuels our imagination when thinking about antimatter as a potential source of energy. In theory, if we could produce enough antimatter, we could harness this annihilation process to provide an enormous amount of energy, far exceeding what we can currently produce with conventional sources like fossil fuels or nuclear power. Antimatter-based energy could offer a clean, nearly unlimited source of power, with the only byproduct being energy itself, unlike the waste and pollution associated with traditional energy sources. This could have profound implications for everything from powering cities to enabling space exploration on an interstellar scale. However, creating infinite energy from antimatter is, at this stage, an impractical goal for a number of reasons. The first and most obvious challenge is the production of antimatter itself. Antimatter is extraordinarily difficult and costly to produce. Particle accelerators, like the Large Hadron Collider, LHC, at CERN, are capable of creating tiny amounts of antimatter through high-energy collisions, but the process is highly inefficient. For every gram of antimatter produced, many times more energy is required to create it than the energy that could be obtained from its annihilation. This means that even though antimatter holds tremendous energy potential, we cannot yet produce it on a scale that would make it a practical energy source. The second challenge lies in the storage and containment of antimatter. Since antimatter annihilates upon contact with matter, it cannot simply be stored in traditional containers. Instead, it must be trapped using powerful magnetic fields in a vacuum to prevent it from coming into contact with the walls of the container. At CERN, the ALPHA experiment has successfully trapped small amounts of antihydrogen for brief periods of time using magnetic fields. However, the quantities involved are still minuscule, and the containment systems required to store antimatter safely are highly complex and fragile. Storing even small amounts of antimatter requires highly advanced technology, and until we can develop more efficient and reliable containment methods, antimatter remains impractical as a viable energy source. Even if we could overcome the challenges of production and storage, there is still the question of how we would efficiently harness the energy released during the annihilation of antimatter. The energy released from antimatter annihilation is so intense that it would require highly advanced systems to safely capture and convert it into usable power. We would need to develop new technologies capable of harnessing this energy without causing destruction, and that would involve breakthroughs in both material science and energy conversion technologies. Additionally, there is the issue of scaling this process to produce the amounts of energy needed for practical use, such as powering a city or spacecraft. Despite these enormous challenges, scientists remain hopeful that advancements in antimatter research will eventually make it possible to harness its energy potential. The ALPHA experiment at CERN, as well as other experiments in particle physics, are laying the groundwork for future discoveries that could lead to more efficient methods of antimatter production, storage, and energy conversion. As technology advances and our understanding of antimatter grows, we may one day find ourselves closer to the possibility of creating near-infinite energy from antimatter. But for now, the idea of generating infinite energy from antimatter remains a distant goal. The energy required to produce antimatter, combined with the complexities of storing and harnessing it, make it impractical for large-scale use in the immediate future. However, the potential of antimatter as an energy source cannot be ignored. If we can find ways to overcome the current limitations, antimatter could become a powerful and nearly limitless energy source, with applications ranging from space exploration to solving the energy crisis here on Earth. In addition to its potential for energy production, antimatter has profound implications for understanding the universe. As we continue to study antimatter and its interactions with matter, we are uncovering fundamental insights into the nature of the universe itself. The matter-antimatter asymmetry, the question of why the universe is made almost entirely of matter, is one of the deepest mysteries in cosmology. Understanding antimatter may help us unlock answers to questions about the origins of the universe, the forces that govern the cosmos, and the fundamental principles of physics. The road to harnessing antimatter as a practical energy source is long and fraught with challenges. However, the work being done in experiments like ALPHA is laying the foundation for future breakthroughs that could one day make antimatter a viable and potentially infinite source of energy. Whether we are talking about energy production, space travel, or a deeper understanding of the universe, antimatter holds the key to many of the questions that have intrigued scientists for generations. So, could we create infinite energy from antimatter? In theory, yes. The energy released when antimatter and matter annihilate is vast, and if we could overcome the challenges of producing, storing, and harnessing antimatter, it could provide a nearly limitless source of energy. But the reality of achieving this is far from certain. For now, antimatter remains an exciting and promising field of research, and while infinite energy may still be a distant dream, the pursuit of this dream is driving some of the most cutting-edge science being done today. The idea of infinite energy, an energy source that never runs out, a power supply that could fuel the future without limits, has fascinated scientists, philosophers, and dreamers for centuries. It's a tantalizing vision, a potential solution to some of humanity's most pressing challenges: the energy crisis, environmental degradation, and even the exploration of the cosmos. But, as compelling as the concept may be, it's not without its paradoxes, and when we turn to experts in the field of physics and energy, we find that the dream of infinite energy is met with both cautious skepticism and careful optimism. At the core of the paradox is one of the most well-established principles in physics, the laws of thermodynamics. These laws, particularly the first and second, suggest that infinite energy is, at best, an impossibility, and at worst, a misunderstanding of the very nature of energy itself. The first law, the law of conservation of energy, states that energy cannot be created or destroyed, only transformed from one form to another. This means that, no matter how much energy we might desire, there is a finite amount in the universe, and it can only change forms. You can't just create energy out of nothing. The second law of thermodynamics takes things even further, asserting that in any process where energy is transferred or converted, some energy is inevitably lost as heat. This leads to the concept of entropy, the tendency for systems to move from order to disorder. Over time, energy becomes less useful, and no process can be 100% efficient. This means that, even if we could develop a process that generates vast amounts of energy, the laws of thermodynamics would still prevent us from creating infinite energy because there would always be inefficiencies. Experts like physicists and energy scientists are quick to point out that while the idea of infinite energy may sound appealing, it contradicts the fundamental laws that govern the universe. According to these experts, the creation of a truly infinite energy source, one that could run indefinitely without any form of depletion or loss, would require rewriting these laws, or at least discovering a new understanding of how they work. As it stands, the physical principles we rely on today strongly indicate that no system can provide energy forever without eventually depleting its resources. However, there are nuances in the expert debate. Many physicists are cautious but not entirely dismissive of the concept of unlimited energy. While they acknowledge that infinite energy, as a literal concept, may not be possible, they also recognize that there are still many frontiers in science where breakthroughs could lead to highly efficient, sustainable, or nearly limitless sources of energy. Antimatter, as we've seen with CERN's ALPHA experiment, represents one of those frontiers. The energy released when antimatter and matter annihilate is far greater than anything produced by conventional energy sources, and though the amounts produced today are minuscule, the potential is enormous. Could antimatter, with advances in technology, become a practical and powerful energy source? While this may not lead to infinite energy, it could offer a solution that dramatically alters the current energy landscape. Other experts suggest that the real future of energy lies in harnessing the power of the cosmos. One concept that excites scientists is the idea of capturing the energy of stars, such as through solar power. The sun, which releases an enormous amount of energy every second, could theoretically provide us with a nearly infinite supply of energy, if we could find a way to capture it efficiently. Some researchers are exploring new forms of solar energy harvesting that might make this more feasible. Likewise, fusion energy, the process that powers the sun itself, has been long regarded as the holy grail of energy production. Fusion promises to provide vast amounts of energy by fusing light elements like hydrogen into heavier elements, releasing tremendous amounts of energy in the process. Although we are still decades away from achieving sustainable nuclear fusion, many experts remain optimistic that this could eventually offer us an energy source that is as close to limitless as we may get. Then there is the concept of space-based energy. Some researchers are exploring the possibility of collecting solar energy in space, where the sun shines constantly without the interference of Earth's atmosphere or the day-night cycle, and transmitting it to Earth via microwave or laser. This could provide an almost continuous renewable source of energy that might approach the concept of infinite energy, though practical challenges remain. However, even with these potential sources of abundant energy, the notion of infinite energy in the strictest sense remains elusive. One thing that experts agree on is that any energy source, whether solar, fusion or antimatter, would have its own set of limits. Even the most promising energy technologies will require time, investment and resources to become viable, and none of them will be without their challenges. While renewable energy sources like wind, solar and hydroelectric power are often seen as a path toward more sustainable energy solutions, they are still subject to constraints such as geographic limitations, intermittency, and environmental impact. No energy source is completely free of trade-offs. Additionally, the pursuit of infinite energy in the context of antimatter and similar high-energy technologies raises a whole new set of challenges related to safety, environmental concerns, and the potential for misuse. The amount of energy produced from antimatter annihilation is so immense that it could have catastrophic consequences if mishandled. Harnessing this energy, while theoretically possible, would require extraordinarily sophisticated containment systems and safety protocols to avoid catastrophic accidents. The risks associated with such high-energy processes could be one of the reasons why experts remain cautiously optimistic, rather than unequivocally enthusiastic. In the end, the idea of infinite energy may be more of a metaphor than a scientific reality. Experts acknowledge that the pursuit of vast, nearly unlimited energy sources is a worthy goal, one that could provide us with sustainable solutions to the challenges of power generation. But they also stress that true infinite energy is unlikely to exist in the way we imagine it. Instead, they focus on breakthroughs that promise to push the boundaries of what we thought was possible, whether through harnessing antimatter, perfecting fusion energy, or tapping into renewable energy sources on a massive scale. For now, the paradox remains. While infinite energy might be a concept beyond our current reach, the search for abundant, sustainable and transformative energy sources continues to push the limits of scientific innovation. Experts may not have the answers to all of our questions, but their work is leading us toward solutions that could one day provide us with a future where energy is no longer a limiting factor, even if it's not quite infinite. The pursuit of infinite energy, or even just vastly more efficient and sustainable energy sources, raises important ethical and practical questions that extend far beyond the laboratory or the theoretical realm of physics. While the potential benefits of such energy breakthroughs are enormous, solving the energy crisis, enabling interstellar travel, and perhaps even addressing global poverty, there are significant concerns about how such power might be used, who controls it, and what consequences might arise from its widespread application. On a practical level, the ethical implications of infinite energy are closely tied to the ways in which we might actually harness and distribute it. If we were to discover or create a virtually unlimited source of energy, it could lead to dramatic shifts in the global power structure. Who would control this new source of energy? Would it be governed by governments, corporations, or perhaps an entirely new system of international cooperation? The distribution of this energy could have profound implications for both global inequality and geopolitical dynamics. Energy is already a major factor in international relations, with countries that control large energy resources often wielding significant political and economic power. The discovery of a near-infinite energy source could exacerbate existing power imbalances, or, conversely, lead to more equitable access to energy if distributed fairly. One of the most pressing ethical concerns revolves around the environmental impact of such energy technologies. While antimatter, for instance, could theoretically provide an incredibly clean source of energy, the methods required to produce and store it are highly complex and energy-intensive. In the short term, creating antimatter requires enormous amounts of energy, many times more than could be extracted from its annihilation. This means that the initial environmental impact could be significant, even if the long-term benefits in terms of clean energy might eventually outweigh the costs. Scientists and policymakers would need to carefully weigh the environmental trade-offs and ensure that any new technology is not only effective but also sustainable. Moreover, the issue of waste would need to be addressed. Though antimatter's annihilation process itself produces no waste in the conventional sense, as it converts mass directly into energy, the infrastructure needed to support such energy production and storage might generate harmful byproducts. For example, the particle accelerators and magnetic containment systems required to produce and store antimatter could require substantial resources and produce electronic or mechanical waste. Likewise, while clean energy sources like solar and fusion hold great promise, they too come with their own sets of challenges, such as the disposal of nuclear waste from fusion reactors or the environmental toll of manufacturing and disposing of solar panels. In addition to environmental concerns, there are potential risks associated with the weaponization of infinite energy. Historically, powerful energy sources have been used for destructive purposes, from the development of nuclear weapons to the exploitation of fossil fuels for military purposes. If a virtually unlimited source of energy were discovered, the temptation to use it for destructive purposes would be considerable. Imagine the potential for weapons powered by antimatter or advanced fusion technologies. This could lead to new forms of warfare, or even the creation of weapons of mass destruction that far exceed anything we can imagine today. It would be critical to establish international treaties, regulations, and oversight to ensure that such technologies are used for peaceful purposes and that the destructive potential of these energy sources is kept in check. The ethical considerations surrounding energy also extend to the social implications. Access to energy is already a major factor in the quality of life for millions of people around the world. In regions where energy is scarce or expensive, people often struggle to meet basic needs such as heating, cooking, and healthcare. The discovery of a nearly infinite source of energy could transform these living conditions and provide a level of economic development that has been impossible until now. However, there's a danger that the new energy resources could be controlled by a few powerful entities, perpetuating inequality and leaving the most vulnerable populations without access to the benefits of this new technology. For infinite energy to truly benefit humanity, there would need to be mechanisms in place to ensure that its distribution is fair and equitable. Furthermore, the practical application of infinite energy could have unintended consequences for economies and industries. Energy production is the backbone of many industries, and sudden access to virtually limitless power could disrupt the global economy. Entire industries based on fossil fuels or nuclear power might face obsolescence, leading to economic upheaval and the loss of jobs in certain sectors. The transition to new energy technologies would require careful management to ensure that the workforce is not left behind and that industries can adapt to new realities. Policies and programs aimed at retraining workers and facilitating the transition would be essential in minimizing social and economic disruptions. There's also the issue of dependency. If humanity were to rely on a single, all-powerful energy source, there could be unforeseen vulnerabilities. What happens if something goes wrong with this energy source? What if it were to be disrupted by a catastrophic event, a technical failure, or an attack? The world would be vulnerable to a single point of failure, which could be far more damaging than the current energy grid, which is distributed and based on multiple sources of power. Developing contingency plans and backup systems would be critical to ensuring the continued stability of society in the face of potential failures. Finally, there's the question of whether we should be pursuing infinite energy at all. While the benefits are obvious, there are some who argue that humanity's pursuit of limitless energy might reflect a broader misunderstanding of the finite nature of the planet's resources. There's a concern that pursuing infinite energy might encourage even greater consumption, leading to a disregard for the natural limits of the Earth and exacerbating environmental destruction. In this view, the real ethical challenge may be learning to live within the planet's means and developing technologies that prioritize sustainability rather than the endless pursuit of growth and power. The ethical and practical implications of infinite energy are vast and complex. As we continue to explore new energy technologies, we must not only consider the scientific and technical challenges, but also the societal, environmental, and geopolitical factors that will shape how this energy is used. The potential benefits are undeniable, but they come with significant responsibilities. It's not just about finding a new source of power, it's about ensuring that power is used wisely, equitably, and responsibly for the benefit of all. The ALPHA experiment at CERN is already making significant strides in antimatter research, but the road ahead is long and filled with both exciting possibilities and considerable challenges. The quest to unlock the secrets of antimatter and harness its potential for energy production, space travel, or even answering fundamental questions about the universe is just beginning. As the ALPHA experiment continues to evolve, the next steps will play a crucial role in shaping the future of antimatter physics and, by extension, our understanding of the universe itself. One of the immediate goals for ALPHA is to continue refining the techniques used to produce and trap antihydrogen, the antimatter counterpart to hydrogen. Creating and trapping antimatter is no easy task, and even the tiny amounts of antihydrogen produced so far require highly advanced technology. In the near future, scientists at CERN will focus on improving the efficiency and yield of antimatter production. Currently, the amount of antihydrogen created in each experiment is minuscule, just a few hundred atoms at most. But the hope is that, as the technology and techniques continue to improve, the amount of antimatter produced will increase significantly, allowing researchers to perform more detailed and accurate experiments. One of the primary goals for ALPHA is to continue studying the properties of antihydrogen in greater depth. Scientists want to understand how antimatter behaves under various conditions, particularly when it comes to gravity. One of the fundamental questions in physics is whether antimatter behaves the same way as matter when subjected to gravitational forces. According to the laws of physics, antimatter should behave similarly to matter, but the lack of experimental data means this question remains open. ALPHA is poised to investigate this question by conducting experiments that examine how antihydrogen atoms respond to gravity. If antimatter behaves differently from matter in this regard, it could have profound implications for our understanding of gravity and the fundamental forces that govern the universe. The next stage of the ALPHA experiment will involve increasing the precision of these experiments. The more precise the measurements of antimatter's behavior, the more useful the results will be in providing insight into the fundamental laws of physics. This will likely involve improving the technology used to trap antimatter atoms for longer periods and reducing the impact of external factors that could skew the data. By achieving even higher levels of precision, ALPHA can help answer some of the most profound questions in physics, such as why there is an apparent imbalance between matter and antimatter in the universe. If scientists can determine whether antimatter behaves in the same way as matter when it comes to gravity and other fundamental forces, they will be closer to unlocking the key to this mystery. As ALPHA pushes forward, another area of focus will be improving the storage and containment methods for antimatter. Currently, the antimatter produced in the experiment must be trapped in magnetic fields, which prevent it from coming into contact with matter. These fields are highly sensitive, and even slight disturbances can cause the antimatter to annihilate. One of the next challenges will be developing better containment systems that can hold antimatter atoms for longer periods and more reliably. This will be essential not only for studying antimatter, but also for any future applications, such as using antimatter for energy production or propulsion. Another avenue that the ALPHA experiment is likely to explore is the creation of more complex antimatter species. So far, ALPHA has focused primarily on antihydrogen, which is made up of an antiproton and a positron. But there is much more to be discovered in the world of antimatter. Could more complex antimatter atoms be created? What other forms of antimatter might exist and how could they be studied? By pushing the boundaries of antimatter production, ALPHA may one day be able to create heavier antimatter atoms. potentially opening up new areas of research and new possibilities for energy applications. In the longer term, the work done in Alpha could have far-reaching implications for a range of fields, from energy production to space exploration. The potential of antimatter as a source of energy is one of the most exciting possibilities, but it remains a distant goal. Before antimatter can be harnessed for practical energy production, we will need to develop ways to produce it more efficiently, store it safely, and convert its annihilation into usable energy. The breakthroughs made at Alpha could one day help us achieve this, but much work remains to be done. One of the more speculative but exciting applications of antimatter is in space travel. As we've discussed earlier, the energy released in antimatter-matter annihilation is so dense that it could revolutionize space propulsion. If we could figure out a way to store and use antimatter efficiently, it could enable spacecraft to travel at speeds far beyond what is possible with current propulsion technologies. Interstellar travel, while still far from our reach, could become a realistic possibility if antimatter propulsion becomes a reality. Alpha is playing a critical role in laying the groundwork for this kind of future technology, even though we are still decades, if not centuries, away from practical applications. Beyond energy and space travel, the work done at Alpha is likely to continue shedding light on some of the most fundamental questions in physics. The imbalance between matter and antimatter is one of the greatest mysteries in cosmology, and by studying antimatter in greater detail, scientists hope to answer this question. If antimatter behaves in the same way as matter under the influence of gravity and other forces, this could provide insight into why the universe is dominated by matter and why antimatter seems to be so scarce. Understanding this imbalance could lead to a deeper understanding of the origins of the universe, the Big Bang, and the forces that shape the cosmos. In short, the road ahead for the Alpha experiment is filled with promise. The work being done at CERN is laying the foundation for the future of antimatter research, and while there are many hurdles to overcome, the potential rewards are enormous. Whether it's in the form of clean energy, advanced propulsion systems, or a better understanding of the universe's deepest mysteries, the Alpha experiment is helping to push the boundaries of what we know about antimatter and its potential applications. While we may not see the immediate practical applications of antimatter in our lifetimes, the research being done today is crucial for paving the way for future generations. Each new discovery, each new breakthrough, brings us one step closer to unlocking the mysteries of antimatter and tapping into its vast potential. And who knows? The future may hold more possibilities than we can even imagine today. As we reflect on the journey through the fascinating world of antimatter, the question of infinite energy, and the groundbreaking work being done at CERN, we're reminded of the vastness of what remains to be explored. The universe, with all its complexity and mystery, is full of possibilities, many of which we have only begun to understand. The pursuit of antimatter research, while still in its early stages, opens doors to a future where we might unlock energy sources that are not just powerful but potentially limitless. Yet, as we stand on the threshold of these discoveries, it's important to remember that the road ahead is long, filled with both obstacles and opportunities. The potential of antimatter and the quest for infinite energy is a symbol of humanity's never-ending drive to push the boundaries of what's possible. For centuries we have strived to understand the universe, from the smallest particles to the farthest reaches of space. And every discovery we make, from the detection of the Higgs boson to the creation of antihydrogen, is a step forward in a journey that could change everything we know about energy, technology, and even the very fabric of reality itself. Yet, for all its promise, the pursuit of infinite energy, whether through antimatter, nuclear fusion, or some other unknown method, carries with it responsibilities. The energy of the future could solve some of the world's most pressing problems, from climate change to the energy crisis to the very survival of humanity. But it could also pose new risks, both environmental and geopolitical. As we develop these new technologies, we must be mindful of the ways in which they could be misused, and ensure that they are harnessed in a way that benefits everyone, not just a select few. This is where the journey of discovery intersects with the ethical considerations that must guide our actions. The universe is full of possibilities, but it's up to us to ensure that we use the knowledge and power we gain wisely. Whether we're contemplating the implications of antimatter as an energy source or dreaming of interstellar travel, we must ask ourselves not only what we can do, but what we should do. The answers to these questions will shape the future of our civilization. As we stand at the edge of a new era of scientific discovery, we must also acknowledge that the answers we seek may not come in the form we expect. The universe has a way of revealing its secrets in unexpected ways, and sometimes the most profound breakthroughs come from areas we hadn't considered. The search for infinite energy, for antimatter, and for a deeper understanding of the cosmos is a journey that will likely take many decades, even centuries, to fully realize. But it is a journey worth taking because it holds the promise of a future beyond our current limitations. The ALPHA experiment at CERN and the research being done in labs around the world are helping to illuminate the path ahead. While we may not have all the answers yet, the progress made so far is a testament to the incredible potential of human ingenuity and curiosity. Every new discovery in antimatter research is a step toward a future where energy is no longer a constraint, where the mysteries of the universe are revealed, and where the possibilities are as limitless as the stars themselves. In the end, the search for infinite energy is more than just a scientific pursuit. It's a reflection of humanity's unyielding desire to explore, to understand, and to improve the world around us. Whether we ultimately find the key to limitless power or not, the pursuit itself has already brought us closer to some of the deepest truths about our universe. And as we continue down this path, we can only imagine what discoveries lie ahead, waiting to be uncovered. So, as we close this chapter, remember that we are not just looking for answers. We are looking to open new doors, doors that lead to a future full of possibilities, a future where energy, like the universe itself, is ever expanding and full of untapped potential. The road ahead may be uncertain, but it is one that holds the promise of a brighter, more sustainable and more exciting future for all of us.